Welcome to week 2, part 3. Now we're going to be talking about something called separation. So, before we get started, a history lesson. It turns out that the actual definition of topology is not that intuitive, and indeed it was debated for a long time. So people had ideas about what they wanted a topology to do, but they hadn't quite figured out what the precise definition was yet. So beyond the basic 3 axiom that you've seen in our definition of topology, there were many others that were proposed in addition, with fancy names like the regularity or the Hausdorff separation axioms. Eventually, things settled and we were left with 2 things. 1, the definition of topology, and 2, the separation axioms. The separation axioms are what we call all the additional proposed axioms that didn't quite make it into the definition. So, to illustrate, if this was the great topological space race, here are the axioms in the definition. And these guys are the separation axioms. Okay, moving on. So, what are these separation axioms? Well, today, they are sort of a list of nice properties that topological spaces could satisfy that help tell us if the spaces are quote, quote, nice or quote, quote, useful. For example, a separation axiom could tell us that a space is metrizable. So if you've taken the metric spaces course, you know what this means. For now, you can think of them as a classification tool for topological spaces. You can use them, like notions of coarseness, to tell topological spaces apart. So there are lots of separation axioms, but in this lesson, we'll be looking at 4 of them. I would say the 4 main ones. There will be a few more that appear in the exercises, if you're interested. So these ones are called T0, T1, T2, and T3. They also have other names, which I will mention if I think it's important. T stands for the German word for separation axioms, and exercise number 1 is pronounce this. I'm not going to do it, but you should. Okay, so let's start with T0. So a topological space X is T0 if for any distinct points A and B in X, there is an open set U such that either A is in U and B isn't, or B is in U and A isn't. So let's take a look at some examples of topologies that are T0 and that aren't T0. So let's start with some of the topologies we know and well. Let's say we have the set dog hat. Do you guys remember some of the topologies we have on sets like dog hat? Well, the easiest one to think about is definitely the trivial topology. So what does the trivial topology look like? Topology. The trivial topology, right, is the simplest topology. It has only 2 open sets, the empty set and the entire set. Now, is the trivial topology T0? Well, in order for it to be T0, I need to be able to separate A and B with 1 open set, meaning I need to find 1 open set that contains A but doesn't contain B, or in this case, contains hat but doesn't contain dog. Is there such an open set? No, right? So the trivial topology is not T0. So we need to do better than that. All right. So let's see, we need to have definitely the empty set as usual, and we need to have the whole set. But since I need at least 1 open set separating hat and dog, let me just say that dog is an open set, right? This topology is actually pretty famous. It's called the Sierpinski topology. And is this topology T0? Well, let's find an open set such that either hat is in it and dog isn't, or dog is in it and hat isn't. Well, the open set that works is this one right here, right? The open set containing dog contains dog and doesn't contain hat. And so this axiom is satisfied. We've checked this. We can check this for any pair of distinct points A and B, but in this topology, there's only one pair of distinct points. So we've checked it for everything. We're done. Okay. So we found one topology that is T0. We found a topology that is not T0. Let's look at another separation axiom. All right, so the next separation axiom is T1. So a topological space X is T1 if for any distinct points A and B in X, there are two open sets, U and V, such that A is in U and B isn't, and B is in V and A isn't. So the difference between T0 and T1 is that instead of being separated by one open set, we're now being separated by two open sets. I've got one that contains a point and not the other, and I've got another that contains the other point and not the first one. So the first thing to note is that if a space is T1, then it's definitely T0, because T0 would be this same statement, except I wouldn't need V. And this would be an OR, and this would be U, right? So T1 is strictly stronger than T0. All right, so let's take a look at an example of a topology that's T1 and an example of a topology that isn't T1. So let's pull up the one that we were looking at before, the Sierpinski topology. So you remember that this is the empty set, the whole set, and circle around one of the points only, so I'm choosing dog. Right, so this is the Sierpinski topology. Now, does this satisfy the T1 axiom? Well, I can find a set U such that dog is in U and that hat isn't, but can I find a set that hat is in but dog isn't? Well, no, right? Because the only open set that hat is in also contains dog. So the Sierpinski topology is an example of a topology which is not T1. All right, let's find one that is. I think you all know, probably you have a guess at least, as to what I'm about to write. So when we talked about topologies way back when, there was one other topology that existed in all sets, and that was the discrete topology, which is just all possible open sets. On 2 points, it's the only one we haven't looked at yet. So this contains the empty set, the set containing everything, the open set containing dog, and the open set containing hat. And now I see that if A is dog and B is hat, then U is the set containing dog, and V is going to be which set? The set containing hat. Right? So we've been able to find two different open sets, one containing one point and not the other, and one containing the other point and not the first one. And thus, we've satisfied T1. So the discrete topology on 2 points is T1. Okay, let's keep going. T2. A topological space X is T2 if for any distinct points A and B in X, there are two open sets, U and V, such that A is in U and B is in V, and U intersect V is the empty set. So the only difference between this example and the previous example is now not only do these sets, U and V, not contain each other's points, they actually don't intersect anywhere. So in the previous example, we could have let's just go back. No worries. In the previous example, we could have had a bunch of points, say, in our set, and we could have had open sets. Let's say I want to distinguish this point and this point. My open sets, which I chose to distinguish those points, could have been this one and this one, say, because this set contains that point, but this set contains the blue point, but not the pink point. And this set contains the pink point, but not the blue point. But these sets wouldn't work for the T2 axiom because their intersection is not empty, right? So in order to satisfy the T2 axiom, what I would need is I would need two open sets which look like this, and this, for example, the intersection of these two sets is empty. All right, so if a space is T2, then it's clearly T1 because the same open sets that work for T2 still work for T1. Let's take a look at a set that satisfies T2. So let's pull up the one that we saw before, the discrete topology. Does the discrete topology satisfy T2? Well, yes, right? Because I have, let's see, empty set, entire thing, dog, and hat. The set that contains hat does not intersect the set that contains dog. So this works for T2. Okay, let's try to find something that isn't T2. Well, I think something that we've already seen before is going to work again. Sierpinski, right? Now I can't separate dog and hat using different sets. So it seems like on 2 points, if a set is T1, then it's also T2, since we've looked at all of the examples. So if you want to find a set that's T1 but not T2, you're going to have to think about some of the examples that you've already seen in the first part of the week 2 lessons. So one of those sets that Todd showed you is going to be T1 but not T2. And if you want to know more about that, you should do the exercises to find out which one it is. Okay, let's move on. I wanted to say one thing quickly about T2. It's that when a space has the T2 property, we say it's a Hausdorff space. So it gets a special name if it's T2. All right, now let's talk about T3. So a topological space, X, is T3 if it's T0 and satisfies something called regularity. Or I guess this should say regular. So a topological space X is T3 if it is T0 and regular, which means for any point A and any closed set C in X, there are two open sets, U and V, such that A is in U and C is in V, and U intersect V is the empty set. So now, instead of thinking about separating points, we're thinking about separating points and closed sets using open sets. All right, so this is like the next level up. Or is it? Why did we have to include T0 here? Can a set be regular but not T0? The answer might surprise you, but let's take a look at an example. So let's bring out the trusty hat and the trusty dog. Actually, I think we're going to need a couple more elements in our set. So let's work on 1, 2, hat, and dog. Okay, so consider the following topology. As usual, we need the empty set, we need the whole space, and we need 2 more. An open set containing hat and dog, and an open set containing 1 and 2. So let's take a look at this space. The first question is it T0? Well, if it's T0, then I have to be able to separate any 2 points, right? So let's take a look at dog and hat. Well, I can't separate those 2 points. Dog and hat are inseparable, right? There's no open set that contains 1, but not the other. So I can't separate this dog from this hat. So the answer is no. The set is not T0. But is the set regular? Well, I need to check. What are my closed sets, first of all? Well, I have 4 closed sets. Remember that the closed sets are complements of open sets. The closed sets are going to be the empty set, which is the complement of the whole thing, which is the complement of the empty set. I need the complement of the set containing 1 and 2. That's going to be the set dog hat. And the complement of the set dog hat is going to be the set 1, 2. So, taking a look at closed sets contained in X and points, I need to be able to separate those things using an open set. So let's take a look at the closed set 1, 2 and the point hat, for example. Well, hat is contained in the open set dog hat, and 1, 2 is contained in the open set 1, 2. So hat and 1, 2 are separated. Dog and 1, 2 are separated by the same argument, and we can flip this around. So if I pick the point 1, for example, hat dog is contained in the open set hat dog, and 1 is contained in the open set 1, 2. So I can separate closed sets from points. So this set is regular. So this is interesting, right? For the axioms T0, T1, and T2, we had that if you are T2, then you're definitely T1. If you're T1, then you're definitely T0. But here we have T3. Now, if you're T3, you're going to be T2, but only because we've included this T0 axiom. Because if you're just regular, you're not necessarily T2, you're not necessarily T1, and you're not even necessarily T0. So somehow, when we start working with closed sets, things kind of go a little bit weird. And we have sort of these separation axioms, like regularity, that don't strictly follow a hierarchy. Okay, so the next thing I want to say is that there are others. So at first, it seemed like we had a hierarchy of separation axioms, but with that last example, we know it's a bit more complicated than that. And we saw that regularity is a separation axiom that doesn't imply T2. Now, there are actually other separation axioms. They all have different names. Some of them are given fractional names like T2 1.5. In the exercises for this part, you'll be able to see some of the other separation axioms, and you'll classify all of the topologies Todd showed in the first part by their separation. So in conclusion, this week we saw lots of examples of topological spaces, ways to take topological spaces and smash them together to make new topological spaces, and ways to classify the properties of topological spaces in terms of these separation axioms. Now it's your turn, so take a look at the exercises, and we'll see you next week. Thanks. Bye.